Let's take a look at a way to calculate the basic probability of a basic poker hand using combinations. So here's a little spreadsheet that I've created for that purpose, and you can create one just like it. I'm dealing with poker. It can easily be done for any other card game or any other type of game as we go through. So what I'm trying to calculate ultimately is a probability of something being true. So what I need to know in terms of hypergeometric distribution is what's the total population I've got going on. I've got that here in column H. So out of 52 cards, if I pick 5, I can use the combinatorial function in Excel to say how many combinations can I make of 5 cards out of 52. So that's your classic 2.6 million hands of cards. And since I haven't filled in the other columns yet, it's calculating a very, very small probability. The probability of any single particular hand in poker is 0.00000038. Very, very small number. So what I've done is I've created what I refer to as 5 card clusters. I don't need clusters that often, but I might need them. So if I'm dealing with a pair in poker, I've got a cluster plus 3 other cards. If I've got 2 pairs, I've got 2 clusters plus 3 other cards. If I've got a full house, I've got 2 clusters plus 3 other cards. The clusters are just a convenience for being able to enter the data I need to do the calculation. So how many clusters there will be depends upon the kind of card you're trying to model. So let's suppose we're trying to model say a full house. So a full house requires me, suppose I want to get aces over kings. So 3 aces and 2 kings would be an example of a full house hand that's very, very good in poker. So the first cluster I'm dealing with is how do I get the 3 of a kind that I need to build something. So out of any given type of card, there are 4 possibilities, 4 aces, 4 kings, whatever it's going to be. So out of 4, how many different ways can I get 3 of them? So 3 is what I'm after. So it turns out there's 4 combinations. Out of the 4 aces in the deck, there's 4 different ways I can get 3 of them as I go through. So that's my first cluster. And of that first card, I'm not just interested in a full house of just aces over kings, but the probability of getting any full house. So in fact, there were 13 different suits available, 13 different cards available to me in the deck, aces up through king. So I can look at how many possibilities I've got going through. So 4 combinations of 13 cards is what I'll want to know when the time comes. So there's my 3 of a kind. To have a full house, I also have to have a pair from a different card. Obviously, I can't have the same card because I've already used up 3 of the one card. So out of 4 cards that are available for some other number, I want to be able to pick 2 of them as I go through. So out of 4 cards, say kings, there's 6 different ways I could draw 2 kings as I go through. And the multiplier I want here is how many different cards were available. Well, we already used up one of the cards to get our 3 of a kind in the first cluster. So in fact, there are 12 different ways that I can get that pair. So there's my full house right there. I've already got my 5 cards. Notice that in terms of my totals, I'm picking 5 cards out of 8. That's my total. And one of the rules of thumb in hypergeometric is try to match the total population and make sure you haven't made a mistake. But as soon as the row 5 matches, I know I'm basically done. But technically, I could say out of the remaining 44 cards, I'm going to pick 0. And there's one way to do that. So now I've got my 52 over 5 matching. That's how I test. So if you test and make sure the numbers here add up to what you said the population was, you'll know you're not making some kind of a mistake as you go through. So there are 24 different hands that I can make that do this, but there's 156 ways to do it. So 156 is because I could have 3 of a kind of any of the cards, as well as 2 of a kind of some other card as I go through. So I'm going to do a bunch of multiplication here. So of the 24 different ways to make the hand a particular hand, so aces over kings would be a particular hand, there's 24 ways to get that. And it turns out there's 156 different combinations of 2s and 4s and 3s and 9s, things of that nature as I go through. So I can calculate a raw probability here. That's just the probability of 24 over the 2.6 million. That's the probability of getting any particular full house hand. So my example of aces over kings, 3 aces and 2 kings, the probability of getting that hand is extremely small, 0.000000923. But when I multiply that probability by the 156 different hands that would in fact be a full house, I get my final probability by multiplying that. And that's 0.00144. So it's a very, very small probability, which is why if you play poker, you're very, very happy to get a full house, because it's a very, very low probability. And poker is basically a game of probabilities. The lower the probability you would have gotten the hand you've got, the more it's worth as you've gone through. So 0.00144 is a very good hand. Let's go through and we can just do one more quick example before I let you go. Suppose I do, in fact, want to get 4 aces. So out of the 4 aces in the deck, I'd like to get all 4. Okay, so that's one way I do that combination. There's only one way to get 4 aces, one number that I'm dealing with for 4 aces. So there's the probability of getting 4 aces. Although if you're quick and notice what I said before, these numbers need to match. That isn't the probability of getting 4 aces. It's the probability of getting 4 aces out of 4 cards, but poker is a 5-card hand. So out of the 48 cards that are left, I still have to pick one more card to make sure I've got 5, and that increases by a factor of 48 the probability. So the probability of getting 4 aces is 0.0001847, much lower than the probability we just calculated for the full house, which is why 4 aces beats a full house. If you just want to know the probability of getting 4 of a kind, you don't care what card it is, then you increase this and say it could have been any of the 13 cards, and the probability jumps to 0.00024. That's still a lot lower probability than the full house. So any 4 of a kind card hand in poker will beat any full house in poker, because the probability of getting the 4 of a kind is so much lower. So you can use a spreadsheet like this. It's simply built on a little logic of the problem. I'm using the combin function quite a bit to calculate the number of combinations. I'm not doing the calculations myself, although the equation isn't that difficult. But you can use this kind of a spreadsheet to calculate the probability of any hand in poker. So if you use this kind of calculation to calculate each type of hand in poker, you could create that hierarchy of probability and rederive, if you will, the rules of poker. The only rule you need in poker is that the less likely hand wins.